What's up? I'm Vin, and today I want to go through an AP Calculus ABBC Unit 3 practice test, and I'll leave a link to a copy of this test in the description below. Now let's get started. So let's start off with the part 1 questions, the multiple choice questions, and we can't use the calculator in this section. So for the first question here, we have f of x equals sine squared of 2x plus 3, and we want to find f prime of x, the derivative. Now when I look at this function f of x, in my head I rearrange this. I think about this as sine of 2x plus 3, and that entire function here is squared. Okay, so when we're going to use the chain rule here, we have to be able to imagine what's the outside function, the middle function, and the inside function. So I look at that function, and this is what I'm thinking about. I'm thinking about the outside function. So the outside function is going to be the square. Okay, we're going to use the power rule to take the derivative of the square on the outside. So we have the square on the outside. The middle function is sine. So that's our middle function. And then our inside function, so the innermost function, is 2x plus 3. So when we use the chain rule, there's a lot of ways we could think of the chain rule, but the shortcut is most helpful here. We say the derivative here in this case is going to be, we're going to take the derivative of the outside, we're going to keep the inside the same, and then multiply by the derivative of the inside. So we're going to start off by taking the derivative of the square. We're going to use the power rule. So we're going to have 2 times, and then we have sine of 2x plus 3. So we have this entire quantity here. And this is now being raised to the first power because we're doing the power rule. We don't actually have to write the power 1 on the outside, but that's the idea for this question. So now that we took care of the outside function, so let's just make some space over here. We're going to move this over. Now we're going to move to the middle function here. So we're going to look next to the sine function. And now we have to take the derivative of sine, which is cosine. So we take the derivative of sine, we get cosine of, and then we have 2x plus 3 because we're going to keep the rest the same. Okay, so that idea of the chain rule, once again, is we take the derivative of the outside, we keep the inside the same, and then we multiply by the derivative of the inside. So now we're going to have to take the derivative finally of the inside function, which is 2x plus 3, and the derivative of 2x plus 3 is 2. So we're just going to tack on this 2 here at the end. So if you forget to write that 2, you'll notice here that choice C is a very dangerous bear trap. Okay, you have to make sure, once again, that you're taking the derivative of each piece that's being chained together here. And now we just combine everything. We're going to have f prime of x equals, we're going to have 2 times 2 is 4, and then we're going to have sine of 2x plus 3, and we're going to have cosine of 2x plus 3. So now we just scan the answer choices here, and this is going to match up with choice D. Now, before we move on, there is another way we could think about this question. We could use the chain rule, the Leibniz notation chain rule. So we have dy dx is equal to dy du times du dx. So this is the most common representation of the chain rule using Leibniz notation. But what you'll notice here is that we actually have 3 functions going on. So we can't necessarily use this notation because, once again, we have a third function. So we're just going to have to write this a little bit differently here. And if we use this second method, I would say something like u is equal to 2x plus 3. That's our innermost function. And then I'm going to name our next function here w. I'm going to say w is equal to, we have sine of u like this. And then the next thing I'll say is that y equals w squared. So if we look here and we just do the substitution, you'll notice that if I plug u in for sine u over here and I plug w into this equation over here, that's going to give us exactly what we started with, the sine squared of 2x plus 3. But now I just have to think about the chain rule a little bit differently now. I'm going to have to think about this in a slightly longer form. This is going to be equal to dy dw, and then multiplied by dw du, and then we multiply again by du dx. So we're going to have to chain these 3 derivatives together. And notice if I actually did the algebra here, these terms would cancel out and it would give me dy dx. So that's how I know this is a valid setup. So now we think about this. I'm just going to make space over here. We're going to take the derivative of each of those pieces. So let's go ahead and do that. So we're going to move this over. We're going to find we have dy dw. So dy dw is going to be, we're just going to use the power rule here. Dy dw is 2w. And then dw du, if we work this out, is going to be equal to cosine of u. And then we're going to find du dx. So the derivative of this u equation is just 2. And now we just plug these 3 derivatives into the formula. So we plug in here, we're going to have dy dx is equal to, we have dy dw is 2w, and then we have times dw du is cosine of u, and then we have du dx is 2. So this solution takes a little bit longer, but this is a more technical solution, and it helps you visualize how the formula is being applied. So now if we were to work this out, we have 2 times 2 is 4. W is equal to, so now we can make a substitution, is equal to sine of u. And then we have cosine of u. But remember, u is equal to 2x plus 3, so we plug in one more time, and we have 4 sine of 2x plus 3, and then we're multiplying this by cosine of 2x plus 3. Now, just know for the AP tests, you have to be able to move very, very quickly. So this second method does take more time, but I definitely feel safer using this method. This method is more reliable. Either way, we're going to get choice D. Question 2, we have g of x is a differentiable function and y equals cosine of g of x to the third. And we want to know what is dy dx when x equals 2. So for this question here, we're just going to take the derivative with respect to x on both sides of this equation. And on the left side, that's going to give us dy dx. And on the right side here, we have to use the chain rule. And notice we have a composition of 3 functions. So we're going to start with the derivative of the outermost function, which is cosine. So we have negative sine, and now we keep the inside the same. We have g of x to the third. So that's our innermost part here. And now we have to multiply everything by the derivative of the inside. But notice that our inside function, we have g of x to the third. So now I'm thinking of the chain rule, but I'm thinking of this representation of the chain rule. When we have f of g of x prime like this, we're doing f prime of g of x, and we're multiplying that by g prime of x. So now we apply that version of the chain rule here, and we're going to have g prime of x to the third, and then we're multiplying by the derivative of the inside, which is 3x squared. Okay, so that's our derivative dy dx. But now to close this out, we just have to plug in x equals 2. So when we plug in x equals 2, let's see what we get. We have dy dx at x equals 2 is equal to, and we have negative sine of g of x to the third. So now we replace x with 2. We have 2 to the third power on the inside. And we have times g prime of 2 to the third power again. And now we have times 3 times x squared. So we're replacing x one more time with 2, and this time squaring it. So now this is going to be, let's see, we have negative sine of g of 2 to the third power is 8. We're just doing 2 times 2 times 2. And then we have g prime 2 to the third power is still 8. And then we have times 3 times 2 times 2 gives us 3 times 4, which is 12. So now I would just move that 12 to the front. We have, think of that as negative 1 times 12. So this is going to be negative 12 sine of g of 8 multiplied by g prime of 8. And if we scan the answer choices here, this is going to match up with choice A. Question 3, we have this equation here, and we're going to find the derivative dy dx. So we're going to use the chain rule again, and our outside function is a power 4. So we're going to use the power rule. We're going to have 4 times x over x minus 1 to the 4 minus 1 is 3. And we're going to multiply this by the derivative of x over x minus 1. So this question here is a combination question. We're going to have to use the quotient rule here to take the derivative of this quotient over here. So for the quotient rule step, you could just use this formula, u over v prime equals vu prime minus uv prime over v squared. And if you struggle with the quotient rule, I highly recommend that you define the u term and the v term. Just think of this as using training wheels on a bicycle. So u equals x, and then we have v equals x minus 1. So u prime is equal to 1, that's the derivative of x, and then v prime is equal to 1. I highly recommend that you use these. Every now and then I still use them because it helps you stay organized in questions like this. So now for our next line, let's go ahead and apply the quotient rule to find the derivative of x over x minus 1. So we have 4 times, and we have x over x minus 1 to the third. And now we're multiplying this by, we apply the quotient rule. And just know the order is very important with the quotient rule because of the subtraction up top. So we have v times u prime. So we're going to have x minus 1 times 1 minus, and then we have uv prime is x times 1. So we're multiplying, we have 1 times x or x times 1. And this is all over, we have v squared on bottom. So the denominator squared, we're going to have x minus 1 squared like this. So now we just have to do the algebra and match it to an answer choice. So we're going to have 4 times, and this rule for fractions is very helpful here. When you have a fraction raised to a power, you could raise the numerator to that power over the denominator to that power. So we have x to the third over x minus 1 to the third like this. And now we're going to multiply this by, just note that up top here, x minus 1 times 1 is just x minus 1. And then we have minus 1 times x is just x. So I'm just imagining here at this step, x minus x is just going to cancel out. And all we're going to be left with up top is negative 1. So we have negative 1 over, and we have x minus 1 squared. So now we just multiply these 3 terms together, and just think of this as 4 over 1. So we're going to do 4 times x to the third times negative 1, and that's going to give us negative 4x to the third. And then on bottom here, we have 1 times x minus 1 to the third times x minus 1 squared, and these two can combine to x minus 1 to the fifth. Okay, so now we just look through the answer choices here, and this is going to match up with choice C. question 4, we have this equation for f of x, and we're given some function values over here and some derivative values, and we want to find f prime of 2. So for f prime of 2, we have to take the derivative of f of x, and notice this time around we have a product. So we're going to use the product rule. And the product rule, we have uv prime is equal to u prime v plus uv prime. So we could define u in this case to be x squared, and we could define v to be g of h of x. Now, if you could do this without writing out the product rule, then great, but I think it just helps here to see this so that when we set it up, it's just clear where everything's coming from. So we have u prime is equal to 2x, and now for v prime, we're going to have to use the chain rule. So we have the derivative of the outside is g prime, we keep the inside as h of x, and then we multiply by h prime of x. So now let's find what is f prime of x. So f prime of x is equal to, so let's say I start with u prime v. So we have 2x times g of h of x, and then we're going to add, we have uv prime, so we have x squared times g prime of h of x, and then times we have h prime of x. So now we're going to plug in x equals 2. So we have f prime of 2 is equal to, we have 2 times 2 times g of h of 2, and then we're going to add here, we have 2 squared, and we're multiplying that by, we have g prime of h of 2 times h prime of 2. Okay, so for this we just have to be very careful making the substitutions. So f prime of 2 is equal to, we have 2 times 2 is 4, and then we have g of h of 2, and now we could use these values they gave us. They told us h of 2 was equal to 5. So now we're going to replace h of 2 with 5. So we have 4 times g of 5 for this first part, and then we have plus 2 squared is equal to 4, and we have g prime h of 2 is still equal to 5, and then we have h prime of 2. So h prime of 2 is equal to 4, so we could just replace that piece with 4. And now we simplify this a little bit more. We have 4 times g of 5 is equal to 3. So we have 4 times 3, and now we have plus 4 times 4, we could just combine these two here to make 16, and then we're multiplying by g prime of 5, which is negative 2. So now we just work this out. Let's see, we have 4 times 3 is 12, 16 times negative 2 is negative 32, and if we do 12 minus 32, that's going to give us negative 20, and that's going to match up with choice B. Question 5, we have this equation here, and we want to know what is dy dx in terms of y. So for this question, we're going to be using implicit differentiation, and I know we're using implicit differentiation here because we can't solve that equation for y. So that's the time to use implicit differentiation, when you can't isolate the y variable. So now what we're doing is we're taking the derivative with respect to x of each term. So we're going to be doing the derivative with respect to x of e to the y, and then we have minus the derivative with respect to x of xy, and then we have this is equal to the derivative with respect to x of the right side, which is just 10. And now for the first term, the derivative with respect to x of e to the y is e to the y, and then times we have dy dx. And the concept behind what's going on here is when we take the derivative with respect to x of e to the y, what we're really doing is the derivative with respect to y of e to the y, but then we're multiplying by dy dx. So we're using the chain rule. And this works out because if you look here, dy over dy cancels, and it will bring you right back to d over dx. But then what we could note is that the derivative with respect to y of e to the y is just e to the y. Okay, so we're using the chain rule every time that we do implicit. So now we'll close this out. And for the next part, this is where things get a little bit tricky. So we're subtracting the derivative with respect to x of xy. So for this part, we're going to be using the product rule. So we could define, let's say, our u term to be equal to x and our v term to be equal to y. So then u prime is equal to 1, and v prime, the derivative with respect to x of y, is 1 times dy dx. So now we apply the product rule, and I'm going to have to write this in parentheses here. So we have minus the derivative with respect to x of xy, we're going to be doing, we have x times dy dx. And then next we have plus 1 times y is y. Okay, the most common mistake with this type of question is that students forget to distribute the negative. Okay, but if you forget to distribute, that's a very, very dangerous bear trap. Okay, so just make sure that you're sending that minus through so that you get your correct answer. So now the derivative of the right side is just 0. So now we do the distribution here, and we're going to have e to the y times dy dx, and then minus x times dy dx, and then we have minus y. Okay, so we're just sending that minus sign through, and this is all equal to 0. So now the rest is just algebra. So we could factor the dy dx out of these two terms, and we could add the y over to the other side because our goal is to solve for dy dx. So now we're going to have an equation where on the right side we have y, and now on the left side we're going to factor out dy dx, and we're going to be left with, in parentheses, we have e to the y and then minus x. So now the next step here, we're just going to divide both sides by e to the y minus x. And now this is going to give us our final answer. So these factors cancel out. And this tells us that dy dx is equal to, we have y over e to the y minus x. And this is going to match up with choice A. Question 6, we want to know the equation of the tangent line to the curve given here at the point where the curve crosses the y-axis. So to write the equation of a tangent line, you need a point and you need a slope. So I'm just going to write the point over here like this, and then our slope we could call our m value. But in calculus, to find slope, you're going to use the derivative to find slope. So we're going to find y prime here, and the derivative of x squared plus 3x plus 4, we're using the power rule, is 2x plus 3. But now we need to know which value of x are we going to plug into the y equals equation and the y prime equals equation. So now we have to think about what does it mean if we're looking at the point where the curve crosses the y-axis. So that's just a really subtle way of saying x equals zeros, because what I'm imagining here is that no matter what curve we have, in this case we have a parabola, but let's say the parabola looks something like this. At the y-intercept, the x coordinate is equal to 0. So we would have x equals 0, and I could just see if we plug in x equals 0 to this equation, the y value is going to be equal to 4. But that's how you find your y-intercept, or where your curve crosses the y-axis, is you plug in x equals 0. So now if we plug in x equals 0, we're going to get y is equal to 4. So that's our point. But now when we evaluate our derivative y prime at x equals 0, this is going to give us 2 times 0 plus 3. So I'll just write this all out. 2 times 0 plus 3, which gives us a slope equal to 3. So that's our slope. And now in calculus, you could use one of two equations to find the tangent line. This is the most popular one you're going to use. Y minus y1 equals m times x minus x1. But in this case here, notice that they gave us the y-intercept. So we could actually use the formula y equals mx plus b, and that's going to get us to the answer right away, because notice all of the answer choices are written in the form mx plus b. So we're going to plug in here, we have y equals, the slope is equal to 3 times x, and then we have plus the b value here for our y-intercept is 4. So now we just scan the answer choices, and choice B is our solution. Question 7, we have this equation here, and we want to know what is the value of dy dx at 1, 0. And we're going to have to use implicit differentiation. So we're going to take the derivative with respect to x of both sides. But for a question like this, what I'm thinking of is the chain rule variant for the derivative of natural log of f of x. And when you take the derivative of natural log of f of x, you get 1 over f of x, and then you multiply that by the derivative of the inside. So you have f prime of x over f of x. So that helps me get started here. We're going to have dy dx is equal to, and we're going to have 1 over the inside. So we're going to have x squared plus y squared on bottom. And then on top, we have the derivative with respect to x of the inside. So we have the derivative with respect to x of x squared plus y squared. So now this will simplify nicely. We're going to have on top the derivative of x squared is 2x. But now for the derivative of y squared, that part we just have to be a little bit careful. We're going to have the derivative of y squared is 2y times dy dx. So we're using the chain rule at this step here. And now we're over x squared plus y squared. So now what we want to find is what is dy dx at 1, 0. So at x equals 1 and y equals 0, we just plug in. We're going to have dy dx is equal to, and now the simplified one we have is on the side here. So we're going to be plugging into this part of the equation. So we plug in, we have x equals 1, that's going to give us 2 times 1, plus we have 2 times y is equal to 0, and we're multiplying that by dy dx. So this piece is going to cancel out entirely because we have a times 0. And on bottom, we have x squared, so we have 1 squared, plus we have y squared is going to give us 0 squared, and this piece will wipe out as well. So now we just have 2 times 1 is 2, divided by 1 times 1 is 1, and 2 divided by 1 is 2, so choice C is our solution. So for questions 8 and 9, we're going to be using this table of values here that has select values of differentiable functions f of x and g of x and their derivatives. And for question 8, we have p of x equals f of g of x, and we want to know what is p prime of 2. So for p prime of x, we're just using the chain rule here. This is f prime of g of x, and then we're multiplying that by g prime of x. So now for p prime of 2, we just plug in x equals 2, and we're going to have f prime of g of 2, and we're multiplying by g prime of 2. So now we just go on that scavenger hunt into the table here, and we have f prime of, and when x equals 2, the function g is going to give us a value here of 1. So we have f prime of 1 times, and now we can just substitute in, what is g prime of 2? So g prime of 2, we go to x equals 2, and g prime is equal to 5. So we're going to multiply f prime of 1 by 5. And now we simplify, we have p prime of 2 equals f prime of 1 is going to be equal to 5. So we have 5 times 5, and that simplifies to 25. So choice B is our solution to question 8. So now question 9, we have if h of x is equal to f inverse of x, then h prime of 12 equals. So now we have to know what is the derivative of f inverse formula. So f inverse prime of x is equal to, we have 1 over f prime of f inverse of x. So this is the formula we're going to be using here. So if we want to find what is h prime of 12, what we're really finding here is 1 over, we have f prime, and then we have f inverse of 12. So now we have to look for what is f inverse of 12. And for this idea, we have to know the relationship between a function and its inverse. So let's say I pick out a random value here, like this value in the table, when we have f of 1 is equal to 3. So if f of 1 is equal to 3, in inverse language, I could say f inverse of 3 is equal to 1. So when I want to find f inverse of 12, I'm targeting the y values in the f of x column. So if you notice here, what we have is we have f of 2 is equal to 12. So we could say f of 2 is equal to 12, and that means in inverse language that f inverse of 12 is equal to 2. So now we could plug into this formula. We're going to have 1 over, and we have f prime of, and this piece here that we just found, we have f inverse of 12, that we're going to replace with 2. So we can make a substitution now. So we're going to have 1 over f prime of 2, and now we look to the table, what is f prime of 2? When x equals 2, f prime is equal to 14. So this simplifies to 1 over 14, and that matches up with choice B. Question 10, we have let f be the function defined by, we have f of x equals this function here. And then we're told that g of x is equal to f inverse of x, and we have g of 4 is equal to 1. We want to know what is the value of g prime of 4. So g prime of 4, we could just use that formula again from earlier. So we have g prime of 4, and to find g prime, that's the derivative of f inverse. So we're going to have f inverse prime at x equals 4, and this, if we use that formula, is 1 over, we have f prime of f inverse of 4. But remember, f inverse is equal to g of x. So when I want to know what is f inverse of 4, that's the same thing as g of 4, which is equal to 1. So now I could just make the substitution here, and I'm going to have 1 over f prime of 1. But now we have to find here, what is f prime of 1? So now we shift our focus to this formula here for f of x. So now we could find f prime of x. F prime of x is equal to, we have 3x squared plus 1. So we're just using the power rule here to take the derivative of f of x. And now to find f prime of 1, we just plug in. We have f prime of 1 is equal to, we have 3 times 1 squared plus 1, which simplifies to 4. So now we could simplify and get our answer. We could say g prime of 4 equals 1 over f prime of 1. F prime of 1 is 4, so our solution here is going to be 1/4, choice A. Question 11, we have a graph of f of x, which is increasing and differentiable, and we also have the line tangent to the graph of f of x at the point 2, 3. And then we have g of x is the inverse of f of x. Which of the following statements about g prime is true? So we're either going to be finding g prime of 2 or g prime of 3. But what we have here is that g of x is the inverse of f of x. So this point over here, we have the point 2, 3, tells us that f of 2 is equal to 3. But in inverse language, if g of x is the inverse of f of x, g of x is equal to f inverse of x, then what we could say here is we could say f inverse of 3 is equal to 2, or if we use g of x, we could say g of 3 is equal to 2. Okay, so this is going to be a very important piece. So now let's see what we could find here based on this. So could we find what is g prime of 2 or g prime of 3? Well, the idea is that we could find g of 3 and g prime of 3, because remember, when you look at an inverse function, the x and the y coordinates switch. So I'm leaning towards choices C and D. That's what I want to explore first. So let's see what happens when we find g prime of 3. So g prime of 3 is going to be equal to, we're going to have f inverse prime of 3. So we have f inverse prime of 3. And if we use that formula for the derivative of f inverse, we're going to have 1 over, and we have f prime of f inverse of 3. And if we just use this definition here, f inverse of 3 is equal to g of 3, which we said before is equal to 2. So now we have this is equal to, I'm just going to write it over here. We have 1 over, we have f prime of 2. So now we have to know what is f prime of 2. And this is why they gave us a graph of the tangent line at x equals 2. So what this means, f prime of 2, is the slope of this tangent line. So the slope of the tangent line, that's what we're looking for, which is going to help us close out this question. Okay, because once again, notice they gave us the tangent line specifically when x is equal to 2 to the curve of f of x. So now to find the slope, we're just going to count the rise over the run. So notice here that we're going to go up. So we're finding the rise over the run. And for this tangent line, the rise, we're going up 1, 2, 3, 4. And we're running across, we're going up 1, 2, 3, 4, and we're going over 1, 2. So the slope of this line is equal to 2. So now we just make the substitution here. Once we know the slope of this tangent line, what that just told us, we could write that over here, is that f prime of 2 is equal to 2. So that is the slope of the line tangent to f of x at x equals 2. So now we just replace this, and we're going to have 1/2, and that's going to match up here. And once again, be careful. We're finding g prime of 3 is equal to 1/2. So don't just get careless here and pick choice A. Okay, choice A is a very dangerous bear trap. Question 12, if you show up to your unit test or your AP test having your formulas memorized, you'll know the derivative with respect to x of tangent inverse x is 1 over 1 plus x squared. And then we have minus the derivative with respect to x of cosine inverse x is negative 1 over radical 1 minus x squared. So if we simplify this, this is just going to be 1 over 1 plus x squared, and then minus changes to plus, and we have 1 over radical 1 minus x squared. So just knowing the formulas for the AP test, you'll see here that this is going to match up with choice D. But before we move on, what happens if we forget one of these derivatives? Let's say I forget the derivative of tangent inverse x. Well, what I would do is I would start off with this equation here, y equals tangent inverse x, and then I would take the tangent of both sides. So we would have tangent y equals x on the right, because if we do tangent of tangent inverse x, the tangent and tangent inverse would cancel, and it would leave us with just x. So that's how we're getting that second equation here. And then from this step, I would draw out a right triangle. So we have this right triangle over here, and I'll label the base angle here as y. And then since tangent y equals x, I could label this side as x and this side as 1, because remember, tangent is the ratio of the opposite side over the adjacent side. So opposite of y is x, and then adjacent to y is 1, and that would give us x over 1, or just x. So now from here, what we could do is take the derivative with respect to x of both sides of this equation, and on the left side, we're going to get secant squared y times the derivative of the inside y is dy dx. And now equals, we have the derivative of x is 1, and we're looking for the derivative of tangent inverse, or dy dx. So we're going to divide both sides by secant squared y. So we have divide both sides by secant squared y, and now secant squared y cancels on the left, and on the right, 1 over secant squared y is the same thing as 1 over cosine squared y, which simplifies to cosine squared y. So we'll have dy dx equals cosine squared y. So now we could just use this diagram over here to find cosine squared y. So if we look here, what we have is two sides of the right triangle. So if we use Pythagorean theorem, we could say 1 squared plus x squared, or just 1 plus x squared, under the square root is our hypotenuse here. So I'm just, once again, using the Pythagorean theorem here. If I say 1 squared plus x squared, this is equal to the hypotenuse, radical 1 plus x squared, squared like this. Okay, so that's how we're getting this part. And the reason why we're finding the hypotenuse is it's going to help us find cosine of y. So now we'll have cosine of y is equal to, and the side adjacent to y is 1, over the hypotenuse is square root of 1 plus x squared. And now this is going to help us find our derivative dy dx. We have dy dx is equal to cosine squared y. So we could take this equation here and just square both sides. And now if we look at this fraction, 1 squared on top is just 1. And if we square the square root on bottom, that's just going to give us 1 plus x squared. So the derivative of y equals tangent inverse x is 1 over 1 plus x squared, which matches what we started with here. But in any case, we're going to get choice D. Question 13, we want to know which functions have the property that f double prime of x equals f of x. So for these Roman numeral questions, you just have to go through them one by one. So for Roman numeral 1, we have f of x is equal to e to the x. And now if we find f prime of x, the derivative of e to the x is e to the x. And if I take another derivative, the derivative of e to the x is still e to the x. So now we have to ask ourselves, is the second derivative here equal to the original function? And yes, e to the x is equal to e to the x. So Roman numeral 1 is good. So now we move on to Roman numeral 2, and in this case we have f of x equals e to the negative x. And this chain rule variant is very helpful for this situation. So when we take the derivative of e to the f of x, this is equal to, we would have f prime of x times e to the f of x. So in this case here, what I'm thinking is we're starting off with f of x equals e to the minus x. So for the first derivative, f prime, we're going to have e to the minus x, but then we're going to be multiplying by the derivative of the exponent, and the derivative of minus x is minus 1. So I'm just going to have a minus in front like this. So now for my second derivative, I'm going to use this chain rule variant again. I have minus e to the minus x, and now I multiply by the derivative of the exponent, which is still negative 1. And now I have the second derivative is we're going to have a negative times the negative is a positive. It's going to give us e to the minus x. So notice that this sign just changes each time, every time you take the derivative of e to the minus x. But notice that f of x and f double prime of x match up. So Roman numeral 2 works out. And now finally for Roman numeral 3, we have this function here. We have f of x is equal to, we have sine x and then minus cosine x. So we'll start off by taking the first derivative. So we have f prime of x is equal to, the derivative of sine is cosine. And then next we have, after this derivative, we have minus the derivative of cosine. So I'll write that off to the side. The derivative of cosine is minus sine x. So what I'm imagining here is we have minus sine x, which changes to plus sine x. So that's our first derivative. And now to take our second derivative, we have f double prime of x equals, the derivative of cosine is minus sine x, and then we have plus the derivative of sine x is cosine x. So now if we factor f double prime of x, we could express like this. We would have minus, and we'd have sine x minus cosine x. So if we look at the original f of x, our second derivative here, notice that it is the opposite of what we started with. It is, we just multiply our first function f of x by negative 1, and it gives us our second derivative. So these do not match. So Roman numeral 3 is out. So it's 1 and 2 only, choice B. Question 14, we have this equation here, and we want to find the third derivative. So this chain rule variant is once again helpful, but I'll write it out a little different this time. I'm going to say e to the kx like this. We're taking the derivative with respect to x is equal to ke to the kx. So that one's going to be very helpful for what we're doing now. So we're going to start off here by taking the first derivative. So we have dy dx equals, and we have the constant in front we just leave alone. We have e to the minus 3x, but now we multiply by the derivative of the exponent, or we just take the coefficient of x, and we have negative 3 in front like this. Okay, so that's going to be our derivative. And now we multiply 2 times negative 3 is negative 6, and we have e to the minus 3x. And now to find our second derivative, and if this notation is a little bit confusing, just know that what we're doing is we're taking the derivative with respect to x of dy dx. And what I'm imagining here, it's kind of like saying d times d is d squared, and then we have d squared y over dx times dx is dx squared. So this Leibniz notation represents our second derivative. Of course, I think f double prime of x is much easier to understand than this notation. But once again, that's the idea behind why it takes that shape. So now we're going to move forward here, and we have negative 6e to the minus 3x, but now we multiply by the coefficient of x, or we could just say the derivative of the exponent negative 3x is still negative 3. So we have times negative 3, and now negative 6 times negative 3 is positive 18, and we have e to the minus 3x. So now for our third derivative, we're going to say d3y like this over dx3 equals, and now we use the chain rule one more time. We have 18e to the minus 3x, and we're multiplying by the derivative of negative 3x, which is negative 3. And now we do 18 times negative 3, that is negative 54, and then we have e to the minus 3x. So we scan the answer choices here, and A is our answer. Question 15, we have g of x given here, and we want to know which of the following is g double prime of 2. So first we have to rewrite that last term as x to the negative second, so that we could use the power rule here. So g prime of x, now we just use the power rule, is equal to, we have 1 over 12 is our constant attached by multiplication, so we just leave it alone. And we're multiplying that by the derivative of x to the 4, which is 4x to the third. We're just using the power rule. And now we have minus 1 over 6 times the derivative of x to the third is 3x squared. And then we have the derivative of x to the negative 2. The negative 2 comes down to give us minus 2x to the negative 2 minus 1 is negative 3. So now we just simplify here. 4 over 12 reduces to 1/3, and 3 over 6 reduces to 1/2. So we could rewrite g prime now as we have g prime of x equals 1/3 x to the third, and then we have minus 1/2 x to the second, and then we have minus 2 times x to the -3. So now for g double prime, we're just going to do the power rule again. So now we have 1/3 times 3 is just 1. So what I'm imagining for this part, when we multiply, we have 1/3 times 3. These are reciprocals, so they just cancel out like this. And it gives us 1 x to the second. And then when the 2 comes down to multiply by the half, those also cancel out to make 1. So we're going to have minus 1 times x to the 2 minus 1 is 1. And now when -3 multiplies with -2, we're going to get plus 6x to the -3 minus 1 is -4. So now eventually we're going to have to plug in x equals 2. So it's going to help to rewrite this as we're going to have x to the second minus x, and then plus we have 6 over x to the fourth power. So now we could plug in 2. We're going to have g double prime of 2 is equal to, we have 2 squared minus 2, and then we have plus 6 over 2 to the fourth power. So now we work this out. Let's see, we have 4 minus 2 is equal to 2, and then we have plus 6 over, and if we do 2 times 2 times 2 times 2, that's 16. And now from here I would divide by 2 on top and bottom just to reduce this a little bit. So we have 2 plus, and we have 3 over 8. So now this is 2 over 1, so I would multiply this one by 8 over 8, just so we have matching denominators. And now g double prime of 2 is equal to, we have 16 over 8 plus 3 over 8, and when we add these two fractions together, that's going to give us 19 over 8, which matches choice D. So now we move on to the free response, and we're still not going to use a calculator in this section. So we have a curve defined by this equation here, and for part A, we want to show that dy dx is equal to this expression here. So we start off by taking the derivative with respect to x of the equation that they gave us. So we have x squared, and then we have plus xy, and then we have plus y squared is equal to 36. So we're starting off here by taking the derivative of x squared, and that's just 2x. And then we have plus, and now we have to use the product rule to take the derivative of xy. So we'll say u is equal to x, and v is equal to y, and then u prime, the derivative of x is 1, and v prime is equal to 1 times dy dx. So now we apply the product rule. We'll say u prime v plus uv prime. So we have 1 times y is y, and then we have plus x times dy dx. So that's the derivative of our middle term there. And then we have plus the derivative of y squared is 2y, and then we tack on dy dx. And then for the right side, the derivative of 36 is 0. So now from here, we want to get all of the dy dx terms on one side, and we want to move everything else to the other side. So here's the dy dx terms. So we're going to move 2x to the other side, so we'll subtract 2x on both sides. And we want to move the y term over, so we're going to do minus y on both sides. So now on the left side here, notice that these terms cancel out, and now we're left with, we have x times dy dx plus 2y dy dx. But all in one step, what we could do is we could factor out dy dx, and we're left with x and then plus 2y. And now this is equal to, we have negative 2x and then minus y. So now to solve for dy dx, we just divide both sides by x plus 2y. So we're doing this on both sides. And now if you look here at the answer that we started with, we're showing that dy dx is equal to this expression here. And notice that we have these two negative terms on top. So what we could do is we could say dy dx is equal to, and now we factor out the negative on top. So we have minus, and then that's going to change the two terms to 2x plus y. And now this is over, we have x plus 2y. So this is the solution for part A. So now for part B, we're going to find the second derivative, and we're going to evaluate it at the point 0, -6. So the first thing that jumps out at me here is that the first derivative, dy dx, is in terms of a fraction. So we're going to have to use the quotient rule to find our second derivative. So this is what you should be thinking about for a question like this. So there's our quotient rule. So looking at this, we're going to say that d squared y over dx squared is equal to, and we have the bottom function here, so we have the low function, and we're going to multiply that by the derivative of the top function. Now this minus in front, a nice little trick is you could just leave that minus on the outside because this is a constant attached by multiplication. You could think of this as -1 times 2x plus y over x plus 2y. So that constant, once again, we could just leave that in front outside of the brackets and apply the quotient rule to just this part where all the positive terms are. So now we're going to have x plus 2y, and then we're going to multiply by the derivative of the numerator here. And the derivative of 2x is 2, and then we have plus the derivative of y is dy dx. So that's the first part here. And now we have minus, and we're going to subtract. We have u is the top, so that's 2x plus y, and then we're going to multiply by v prime, which is the derivative of the bottom. So we're going to have 1 plus, and we have 2 times dy dx. So that gets us started for this question. But now we're dividing everything by v squared. So that's the denominator squared. So that's going to go on bottom here. We're going to have x plus 2y squared. So now at this step, we should remember that we're finding the second derivative and we're going to evaluate it at the point 0, -6. And notice that our second derivative includes dy dx in this expression here. So what I would do is I would find dy dx at 0, -6. And then whatever value I get for this, I'll be able to plug this into this expression when we want to evaluate the second derivative at 0, -6. So first, let's plug that into the first derivative. And we're going to get minus, and then we have 2 times x, but we have x equals 0. And then we have plus y, and y is equal to -6. And we're dividing by, we have x plus 2 times y, and then y is equal to -6. So the 2 times 0 cancels, this 0 just wipes out. And now we have minus, and then we're going to have -6 over 2 times -6 is -12. So this is going to simplify here. We're going to have a negative over negative going positive. But then we have a minus in front, and 6 over 12 reduces to a half. So we have -1/2. So now we could evaluate the second derivative at 0, -6. So we have the second derivative at 0, -6 equals, and we have this minus sign on the outside. And then we have x plus 2y. So we're just going to start plugging in here. We're going to have 0 plus 2 times -6. And then this is going to get multiplied by, we have 2 plus dy dx. But we just found dy dx at 0, -6 is equal to -1/2. So we could just plug in -1/2 at this step. So we have this, and then we have minus 2x plus y. So we're going to have 2 times 0, and then plus -6. And then this gets multiplied by, we have 1 plus 2 times, and dy dx once again was -1/2 at 0, -6. So we just plug in here like this. And then notice here, 2 times -1/2 is equal to -1. And 1 minus 1 is just going to simplify to 0. So this entire product here is just going to cancel out. And that's just going to make it much nicer to simplify at the very end. So now in the denominator, we plug in, we have 0 plus, and then we have 2 times y. So we have 2 times -6. And then this whole quantity is being squared. So now we evaluate this, and we're going to have minus, and then up top here, we have 2 times -6 is -12. So we have -12. And then 2 plus -1/2 is 1.5. And 1.5, I could just say, is 3 over 2. So I'm going to multiply this by 3 over 2. And then from here, we have, this is all over, and we have 2 times -6 in parentheses, and this is being squared. Now, just know on the AP test, you're allowed to just leave it in this form here and not simplify everything, but it bothers me to leave it in this form. And just for the sake of the video here, I'm just going to go ahead and close this out. But if it were the AP test, once again, you don't actually have to simplify any of this stuff. You could just leave it in this expanded form here. And what we're going to have from this step, I'm doing 12 divided by 2 is 6. And then from here, we're going to have negative, and then we have the fraction here. -6 times 3 is -18. And then we have -12 squared is 144. So now we have a minus going to plus. So now we have 18 over 144. And then for this, I would just start reducing here. So I would start by dividing the top and bottom by 2. So divide the top by 2 and the bottom by 2. And this reduces to 9 over 72. But notice that both of these numbers are divisible by 9. So if we divide the top and bottom by 9, this is all going to simplify to 1 over 8. So now part C, we want to determine whether the lines tangent to the curve at the x-intercepts of the curve are parallel, and we have to give a reason for our answer. Well, since we're dealing with x-intercepts occur when y is equal to 0. And if we're trying to show that the lines tangent are parallel, that means we need to be able to show that the lines have the same slope. So we're going to be targeting the slopes of the lines. So that means we're going to have to plug into the first derivative. But all we know right now is that we're working with x-intercepts, which occur when y is equal to 0. So we could say here that the x-intercepts imply that y is equal to 0. And if y is equal to 0, we plug that into the equation we started with. We're going to have x squared, and we have plus x times 0, plus, and then we have 0 squared is equal to 36. And now this equation here simplifies to, we'll have x squared equals 36. And if we simplify this, we just take the square root of both sides. We're going to get our x values here. X is equal to plus or minus 6. So now that we know both x-intercepts, we could plug them into the first derivative, and that'll tell us the slope of the line's tangent at the x-intercept. So first, let's find the derivative at 6, 0. And if we plug into the formula here, we're going to have negative, and then we have 2 times 6, and then plus 0, over, and then we have x, so we're going to have 6 plus 2 times 0. And this simplifies, we're going to have negative, and we have on top 12, and then on bottom we have 6. So this simplifies to -2. And now for the derivative at the second x-intercept, we're going to have dy dx at negative 6, 0. When we plug in here, we have the minus in front, and then we have 2 times x, and x is negative 6, and then we have plus y over, and then we have x is negative 6 plus 2 times y, and y is equal to 0. And this one simplifies too. We have minus, and then on top we have minus 12 over negative 6. And now we have a negative over negative going positive, but we have a minus in front. So this is going to make minus 2. And notice that we have matching slopes. So now we just have to write a sentence connecting all of this. And notice that when we plug in the x-intercepts to the derivative, we get negative 2 for both of them. So what this tells us is that the slope of the lines tangent to the curve at the x-intercepts are equal, which means that the lines are parallel. And now one last thing to mention before we move on, just note the 3 dots in this triangular formation means therefore. So now for part D, the last part, we want to find the coordinates of P in quadrant 2 where the line tangent to the curve is vertical. So just know anytime you have a vertical tangent line, that's going to occur when your slope is undefined. So I always think of slope guy, and the guy I'm about to draw, if this guy gives you a nightmare, then I apologize in advance. But this guy is really helpful for knowing what you need to know about slopes. So when you have a positive slope, your line goes up. When you have a negative slope, your line goes down. And when you have a vertical line, that's an undefined slope. And a horizontal line has a 0 slope. So when we have a vertical tangent line, that means our slope is undefined. And when you have a fraction, so what I'm thinking about here is when we have a fraction, that means that the value on bottom is equal to 0. So we could have some constant on top, but we're going to be dividing by 0 like this. Okay, so the idea is when we have a vertical tangent line, so I'll write that over here, a vertical tangent line. So a vertical tangent line implies that the denominator of dy dx is equal to 0. So the vertical tangent line allows us to set up x plus 2y is equal to 0. And now what we could do is solve this for x. So this tells us that x is equal to minus 2y. I'm just subtracting 2y on both sides. So now with this information here, what we could do is we could plug it into the original equation and find the coordinates of point P. But be mindful here that we are in quadrant 2. So another thing that I'm thinking of, and I'll put the thought bubble over here, is when we're in quadrant 2, we're in a situation here where the x is negative and the y is positive. So that's just going to help us make sure we find the right answer. So now we plug in, and we're going to have, instead of x squared, we're going to have negative 2y, and that's being squared, plus x times y. So we're going to replace x with negative 2y, and we're going to multiply that by y, and then we have plus y squared is equal to 36. So now this equation is in one variable, so we could solve it for y, and negative 2y times negative 2y is 4y squared, and then we have negative 2y times positive y is minus 2y squared, and then we have plus y squared is equal to 36. So now we just combine these like terms. We have 4 minus 2 is 2, and then 2 plus 1 is 3. So we have 3y squared on the left is equal to 36. So we could divide both sides by 3, and we're going to get over here, we're going to have y squared is equal to 12. So now we take the square root of both sides, but now we're going to use the idea that we are in quadrant 2 to find just the positive root here. So technically I would have to say y equals plus or minus square root 12, and we'll just make this a little bit neater. We would have to say y equals plus or minus root 12, but since we're in quadrant 2, the y value is going to be positive. So we could say y is equal to square root 12. And now to find the corresponding value of x, we could just plug into this equation that we have boxed off here, and we're going to say x is equal to, and we have negative 2 times our y, and our y is radical 12. So now the coordinates of P, we could just say here, are equal to, we're going to have negative 2 radical 12, comma, radical 12. And just know for the AP test, we don't actually have to simplify our radicals, so we could leave our answer like this. Now, one last thing I would do for insurance points here is I would plug xy back into the original equation just to make sure that it equals 36. So if we replace x with negative 2 radical 12, we'll have negative 2 radical 12, and then this is being squared, and then we have plus x is negative 2 radical 12, and we're going to multiply that by y, which is radical 12. And then finally, we're going to add this to y squared, and y is equal to radical 12. And this is being squared, and let's see if this is equal to 36. So now we could do negative 2 squared is 4, and then radical 12 times radical 12 is 12. So we have 4 times 12, and then we have a positive times a negative, so we're going to have minus, and we have 2 times radical 12 times radical 12 is 12. And then we have plus radical 12 squared is 12, and once again, let's see if this is equal to 36. So now we get 48 minus 24 plus 12 is equal to 36. And then this is going to give us here, we're going to have 24 plus 12, which gives us 36 equals 36. So our point here checks out.